have pages and extents, database file and the file groups, extent allocation and free space, table and index architecture, transaction log architecture. The fundamental unit of data storage in SQL Server is the page. The disk space allocated to a data file, be it MDF or NDF in a database, is logically divided into pages numbered from 0 to n. The disk operations in a database happens mainly at the page level. Extents are a collection of 8 continuous pages and are used by SQL Server to efficiently manage the pages. All pages are stored in extents. In SQL Server, the page size is 8K. This means SQL Server database has got 128 pages per megabyte. Each page begins with a 98-byte header that is used to store system information about the page number, the page type, the amount of free space on the page, the allocation unit ID of the object that owns the page. The following table shows 8 types of pages in the data file of SQL Server. Primarily, we have data page, index page, text and image page, GAM and SGAM, page free space, index allocation map, bulk change map, and differential change map pages. Database generally stores the data of a table except the text, image, and end text. The index page contains the index entries. The text, end text, and image data are stored in text and image page. Extent allocation information is stored in GAM and SGAM. Information about the free space available on the pages is stored in PFS. Information about which extents are used by a table or index is stored in index allocation map page. Information about the extents modified by bulk operations since the last backup log statements are stored in bulk change map, and information about the extents that have changed since the last database backup is stored in differential changed map. Extents are the basic unit in which the space is allocated to tables and indexes. An extent is 8 continuous page on 64 KB. This means SQL Server database have 16 extents per megabyte. To make its space allocation efficient, SQL Server does not allocate the entire extent to tables with small amount of data. SQL Server has got 2 types of extents. One is a uniform extents and which is other is a mixed extents. Uniform extents are owned by a single object, and all 8 pages in the extents can only be used by the owning object, whereas mixed extents are shared by up to 8 objects. So for instance, when you create a new table, a page is allocated to the new table from a mixed extents. As the table or index grows to a point, then where the 8 page can be allocated, then the table is switched from mixed extent into uniform extents. An index allocation map page maps the extents in 4 GB part of a database file used by an allocation unit. The allocation of pages to a table or an index or an indexed view partition is managed by a chain of IAM pages. An allocation unit is of 3 types: in-row data allocation, log data allocation, row overflow data allocation. The in-row data allocation holds the partition of a heap or an index. The log data holds a large objects like XML, var binary max, and varchar max. The row overflow data holds the variable data stored in varchar, nvarchar, var binary, where the column exceeds 8060 bytes row size limit. So this implies that we can have a row size of maximum of 8060 bytes. Each partition of a heap or index contains at least an in-row data allocation. That it may also contain a log data or row overflow data allocation depending on the heap or index schema. You can view the sys allocations of what allocations are used by an object using a schema view, which is sys.allocation units catalog view. The database, next we cover is database files and the file group. Microsoft SQL Server maps a database over a set of operating system files. Data and log informations are never mixed on the same file, and individual files are only used only by one database. SQL Server database primarily have three kinds of file. One is a primary data file, other is the secondary, and the third one is a log. The primary data file is the starting point of the database and points to other files in the database. Every database has got one primary data file. The recommended file extension for primary database is MDF. The secondary data file comprises of all the data files other than the primary data file. The recommended extension for the secondary data file is .ndf. The log files hold all the log information used to recover the database. There must be at least one log file for each database, although there can be more than one. The recommended extension for log is LDF. SQL Server does not enforce these extensions, but these extensions are recommended to help identify the use of these files. In the SQL Server, the location of all the files in the database are recorded in both the master database and the primary file of the database. Most of the time, the database engine uses the file location information from the master database. Each of these files has got two names. One is a logical name, the other one is an OS file name. The logical name is a name used to refer to the file in all transact SQL statement. The logical file name must conform to the rules for SQL Server identifiers and must be unique to the database. The OS file name is the name of the physical file. It must follow the rules for Microsoft Windows OS file naming convention. Next, database file groups. Database files can be grouped together in file groups for allocation and administration purpose. Some systems can improve their performance by controlling the placement of the data and the indexes onto a specific disk drives. File groups can aid this process. The systems administrator can create file group for each disk drive, then assign specific tables and indexes to specific file group. No file can be a member of more than one file group. Log files are never a part of file group, and log space is managed separately from the data space. There are two types of file group. One is primary, the other one is user defined. The primary file group contains the primary data file and any other file not specifically assigned to another file group. All pages from the system tables are allocated in the primary file group. User-defined file groups are created by user, and we can use the file group while creating specify using the file group keyword in the create database or alter database statement. If no default file group is specified, the primary file group is taken as the default when we create an object. One file group in each database operates as a default file group. So when SQL Server allocates a page to a table or index for which no file group was specified, when they are created, the pages are allocated from the default file group. Extend allocations and free space. Microsoft SQL Server contains data structure that back extend allocation and free spaces. There are few benefits of this architecture. The free space information is densely packed, so there are relatively few pages containing this information. This also increases the speed by reducing the amount of disk reads necessary to retrieve the allocation information and increasing the chance the allocation pages will remain in the memory, eliminating even more reads. Most of the allocation information is not chained together, which simplifies the maintenance of the allocation information. Each page allocation or deallocation can be performed quickly, decreasing the contention between the concurrent tasks needing to allocate or free the pages. SQL Server uses two kinds of allocation map. One is GAM, the other one is SGAM. GAM refers to Global Allocation Map. This page records what extents have been allocated. Each GAM covers 64,000 extents or nearly 4 GB of data. The GAM has one bit for each extent in the interval it covers. If the bit is 1, the extent is free. If the bit is 0, the extent is allocated. The shared global allocation map records what extents have been currently used as mixed extents and have at least one unused page, so that when we create a new table, SQL Server can place the table to begin with on the SGAM or the where the space is available. Each SGAM covers 64,000 extents or nearly 4 GB of data. The SGAM has got one bit for each extent in the interval it covers. If the bit is 1, the extent is being used as a mixed extent and has free spaces. If the bit is 0, the extent is not used as a mixed extent, or it is a mixed extent whose pages are all in use. Next, there is a special page called page free space. This records whether an individual page in a heap or an in-text or text or image column has been allocated and the amount of free space on each page. Each PFS page covers approximately 8,000 pages. For each page, the PFS has a bitmap recording whether the page is empty or it's full till 1 to 50%, or it's 51 to 80% full, or 81 to 95% full, or 96 to 100% full. After an extent has been allocated to an object, SQL Server uses the PFS page to record which pages in the extent are allocated or free and how much free space is available for use. This information is stored when SQL Server has to allocate a new page or when it needs to find a page with free space available to hold a newly inserted row. A PFS page is the first page after the header page in the data file. The next comes is the GAM, which is the page number 2, followed by SGAM, which is the page number 3. That is the PFS page approximately 80,000 pages after the first, and there is another GAM after 64,000 extents after the first GAM on the page 2, and another GAM each 64,000 extents after the first GAM, SGAM on page 3. Table and index architecture. Objects in SQL Server database are stored as a collection of 8 KB pages. In SQL Server, table and index pages are contained in one or more partitions. A partition is a user-defined unit of data organization. By default, the table or an index has got only one partition that contains all the table or index pages. The pages of a heap or clustered index are managed in one or more allocation unit depending on the column type in the data rows. The partition resides in a single file group. A table is contained in one or more partitions, and each partition contains data rows in either a heap or a clustered index architecture. To view the partition used by a table or index, we can use sys.partitions catalog view. SQL Server table uses one of the methods to organize their data pages within a partition. Either it uses a clustered table. So a clustered table have a clustered index. The data rows are stored in order based on the clustered index key. The clustered index is implemented as a B-tree index structure that supports fast retrieval of the rows based on their clustered index key values. And the pages at each level of the index, including the data pages in the leaf level, are linked in a doubly linked list. In case of heap, the tables have no clustered index. The data rows are not stored in any particular order. And there is no particular order to sequence of the data pages. Data pages are not linked in a linked list. Indexed views have the same storage structure as clustered index. When a heap or clustered index has got multiple partitions, each partition has a heap or a B-tree structure that contains a group of rows for that specific partition. For example, if a clustered index has got 4 partitions, there are 4 B trees, 1 in each partition. Non-clustered index have got B-tree index structure similar to one in a clustered index. The difference is that the non-clustered index do not affect the order of the data rows. The leaf level contains the index row. Each index row contains the non-clustered key value or a row locator. XML indexes, one primary and several secondary XML indexes can be created on each XML column in the table. An XML index is a shredded and a persistent representation of the XML binary large objects in the XML data type column. To view the information about the XML indexes, we can use the system catalog sys.xml_indexes or sys.internal_tables catalog views. Next, transaction log architecture. Every SQL Server database has got a transaction log that records all the transactions and the database modifications made by each transaction. The transaction log is a critical component of a database, and in the case of a system failure, can be the only source of recent data. It should never be deleted or moved unless the consequence of doing that are fully understood. SQL Server transaction log operates logically as if the transaction log is a string of log records. Each log record is identified by a log sequence number. Each new log record is written to the logical end of the log with an LSN that is higher than the LSN of the record before it. Log records are stored in a serial sequence as they are created. Each log contains the ID of the transaction that it belongs to. For each transaction, all log recorded associated with the transactions are individually linked in a chain using backward pointer that speeds up the rollback of the transaction. The transaction log keeps the before and the after image of the data that is being modified. Write-ahead transaction log architecture. SQL Server uses write-ahead log mechanism. A write-ahead log guarantees that no data modifications are returned to the disk before the associated log record is returned to the disk. This maintains the asset properties for a transaction. To understand how the write-ahead log works, it is important for you to know how data modified is returned to the disk. SQL Server maintains a buffer cache into which it reads the data pages, and when data must be retrieved, data modifications are not made directly to the disk, but they are made to the copy of the page in the buffer cache. The modification is not returned to the disk until a checkpoint occurs in the database, or the modification must be returned to the disk so that the buffer can be used to hold a new page. Writing a modified data page from the buffer cache to the disk is called flushing the page. A page modified in the cache but not yet returned to the disk is called a dirty page. At the time a modification is made to a page in the buffer, a log record is built in the log cache, and that records the modification. This log record must be returned to the disk before the associated dirty page is flushed from the buffer cache to the disk. If the dirty page is flushed before the log record is written, the dirty page will create a modification on the disk that cannot be rolled back if the server fails before the log record is written to the disk. SQL Server has a logic that prevents a dirty page from being flushed before the associated log record is written. A log record are returned to the disk when the transactions are committed, checkpoints, and the active portion of the log checkpoints flushes the dirty data from the pages from the buffer cache of the current database to the disk. This minimizes the active portion of the log that must be processed during a full recovery of a database. SQL Server database engine divides each physical log file internally into a number of virtual log files. The virtual log files have no fixed size, and they are no fixed number of virtual log for a physical file. The database engine chooses the size of the virtual log file dynamically while it is creating or extending the log file. The database engine tries to maintain a small number of virtual log files. The size of the virtual log files after a log file has been extended is the sum of the size of the existing log and the size of the new file increment. The size or the number of the virtual log file cannot be configured or set by the administrators. So next we'll be covering the logical database architecture, under which we'll be covering the table and the